Okay, so the next thing we talked about was we introduced the chain rule for derivatives, and a good way to introduce chain rules to work with the functions e to the x and natural log x first, and then apply the chain rule to other functions. So first, let's look at e to the x and consider the derivative of it. So if we just look at this thing visually, over here, it's always increasing, so the derivative should always be positive. But over here, the slope is very flat, right? The slope we would say is close to zero. And then as you progress, the slope gets steeper and steeper and steeper and steeper and steeper. Well, let's look at the function. Over here, the function its output is close to zero, and as you move left, it gets even closer to zero. But as you move right, the output gets bigger and bigger and bigger and bigger. So the output of the function is exactly following the path of the slope of the function. They're the same. So what we say is d dx of e to the x just equals e to the x. So this number e, it turns out to be the base that leads to a function that is its own derivative. It's exactly the perfect base, 2.71828, blah, 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 that leads to a function that is its own derivative, and it makes sense visually if you think about the outputs of the function versus the slope of the function. Now, natural log x ends up looking like this, something like this. Okay, so if we look at natural log x, it's always increasing as well, so the derivative should always be positive. But what we notice is it's very steep, close to zero, and then quickly it flattens out, right? So we would want a derivative that's big and positive, and then that positive number is going to start decreasing as the slope decreases, and then it's going to approach zero as this flattens out. So if we were to draw that, it would look something like this, which to me looks like part of the 1 over x function, right? The positive side of 1 over x. So if we say d dx of natural log x, just kind of by a quick visual explanation, that is 1 over x. Okay, so you want to understand those visual explanations of e to the x and natural log x, but once you know them, we can just memorize those derivatives. But what about e to the negative x? What about e to the negative x? So, okay, oh my gosh. Sorry. Okay, e to the negative x. So the deal with this is it is always decreasing, so the derivative always needs to be negative, and also it starts by decreasing steeply and then it steadies out over time. So if we were to think about this, it's not its own derivative because it's positive and the derivative's negative, so that doesn't work. But if we were to flip this over, and if we were to look something like this, that would make sense, right? Because over here, okay, it's negative, but it's big. The function is decreasing steeply. And then it's starting to approach zero, just like the function's steepness is approaching zero, but it's always negative, right? So what we would say is d dx of e to the negative x is actually negative e to the negative x. And this is our introduction to the chain rule. So if we think about the derivative of e to anything, we're going to say it's e to any, we'll say e to the blah, okay? So if we're going to do the derivative of e to the negative x, okay, we say, what is the derivative of e to the blah? Well, it's e to the blah, whatever the blah is, negative x. But then we have to multiply by the derivative of blah. What's the derivative of blah, negative x in this case? Well, that's just negative 1, so we just throw a negative out front. Right. So, and again, this makes sense based on the visual representation of e to the negative x and how its derivative must then look, right? It makes sense that it would be negative e to the negative x. So then for another example, well, let's do d dx of e to the x cubed. Okay. Well, the derivative of e to the blah is e to the blah multiplied by the derivative of blah. What's the derivative of x cubed? It's 3x squared. Okay, so now we're really cruising. We can think about, well, what about the derivative of natural log of sine x? Let's do that. Natural log sine x. Okay, we're going to take the derivative of this. Okay, well, the derivative of natural log of blah is 1 over blah, multiplied by the derivative of blah, in this case, cosine. And what's cosine over sine? Well, that's just cotangent. So now we can find derivatives like this using our chain rule. There are a lot of examples of these on your study guide, so you really should just look for those videos if you're struggling on the study guide at all. But I'll do one more. I like doing secant because this really demonstrates the chain rule in a different way, because the derivative ends up having two places where the input goes. So the derivative of secant blah, as we showed in another video, is secant blah times tangent blah. So you really need to make sure this 3x goes with both pieces of the derivative. That's a common error to not include it in both pieces. So you want to make sure you do that. So we have secant blah times tangent blah. Then we have to multiply by the derivative of blah, which is just 3. So there's our final derivative, 3 secant 3x times tangent 3x. If you're looking for more examples of complicated chain rule problems, you can look at Mr. Allaire's videos for the Chapter 2A study guide, and I encourage you to review this video as well.